Oh, I need you at all my talks. Thank you. Thanks, everyone. Thank you for coming down. Thank you. First of all, thank you for being at the conference. I appreciate that from everyone. And second of all, thank you for coming and listening to me speak. I know that we've not had a huge amount of, or you've not had a huge amount of notice about this. Unfortunately, someone was sick, and you're stuck with me as the step in. So it might be a little bit rough. Feel free to ask as many questions as possible. I'm going to cover as much as I can do. Again, if I go over something and it's not clear what I'm talking about, do just stick your hand up. So today I'm going to be talking about platforms of valuable AI products, because it's all well and good to say we should make the smartest new LLM model, whatever, but how do we actually use them to do something useful? So rather than this being a thing in which I build up subtly and gradually build evidence and make a point, I'm making a point up front so no one can miss it. The key message, the more experiments we do, the more likely we're going to do something valuable. So in any system, when we don't understand what's going to happen, we experiment to learn about it. This is the case in data, machine learning, AI. We need to be able to experiment. Therefore, it's super important to have systems, and by systems, I mean combinations of people, tools, and processes to do something. Systems, tools, and processes to do experiments. Each element of this, the more experiments we do, the more likely we are to do something valuable, something useful. And again, I'm going to talk generally about more simple use cases, e-commerce, making money, etc., because it's a bit more straightforward. But this applies to government, NHS, all kinds of other things in which the outcome is often more important, but less easy to talk about in a simple talk like this. So one of the nice things about my experience of working in businesses and commerce is we're optimizing for money goes up. Not always great, but simple. So who am I? I'm John. As many of you may have realized, I've got a PhD in molecular genetics. I moved out of that to move into data science when I graduated. I'm the chair of PyData London. I'm an organizer of PyData Manchester. I organise the Field of Play conference, which is sports analytics, held in Manchester. Get involved. And I am an independent consultant working for my own company, PDFTA. So if anyone wants to build valuable machine learning, data, or AI products, please pay me money. There we are. I'm not a salesperson. So why should you listen to me? Why should you care? One, I'm very smart. Please believe me. But I've worked on some projects in the past. So as an example, this is not an exhaustive list. Search ranking in e-commerce, recommendations models also in e-commerce. So, like some of these are from massive companies you will have heard of and shops within the UK. Building e-commerce ML platforms. Now you might think that's very similar to building e-commerce models. It is. I've barely done any modeling in the past 3 years. It's all about how to build systems and which models can be run on. Worked on insurance pricing systems and worked on high throughput prediction systems in cybersecurity to classify 5 billion data points a day. A lot of these weren't really difficult machine learning challenges or AI or math challenges, although one or two were. Most of it was how do we take something and incorporate it into a business process to achieve an outcome. So, sorry, I'm just going to make sure I've got my little time on. Never mind. So, the cost of not iterating. You'll be familiar, I think, or a lot of people will be, with concepts like the software development life cycle, DevOps, etc. These have been around for a little bit, and core to a lot of these is we do something, we improve it, we iterate, etc., etc. One of the older versions of these is as data scientists, the scientific method. We propose a hypothesis, we use data to experiment and try and disprove the hypothesis. We learn from that, then we propose a new hypothesis, and from there our understanding grows and grows and grows. So every element of what we do within data product work, whether it be data science, machine learning, etc., engineering, it's all come to be part of it all requires iteration to be pretty important, important fundamental part of it. So, behold the simple reference architecture. This is my comfort reference architecture. It's from Google's MLOps Stage 2. Now, you may look at it and think, John, that isn't very simple at all. And you'd kind of be right, you'd kind of be wrong. It's right in that, yeah, there's a lot going on. It's not, I don't think it's simple, but it's a simplified version of there's an awful lot of complexity hidden behind this abstraction. And the point I want to make here is there's a lot that goes into building a complex machine learning system. Leanne, who gave the keynote this morning, she and I have spoken a lot over the years, and I've learned a lot from her. And we've had some really, really, lovely chats in which I've learned a lot. But one of the key things, and is she's covered a lot of what I want to talk about. You've got to do the boring stuff to get value from it. So, yeah, before I go off on a tangent about that, we've got the reference architecture. It's important we build appropriate architecture to underpin what we want to do. Now, I'm not going to go through the entire reference architecture. If you Google MLOps Stage 2, GCP, then you should be able to find a whole article with this that goes in very nicely. But what I want to say is, if we want to build something like that reference architecture, say we've got a crack team of fantastic engineers, really mature processes, all the wonderful tools, it's going to take us ages. It's going to take 6 months, 12 months, 18 months. Who can say it's going to take ages? What we need to do is make sure we're delivering the incremental steps. So every little bit we deliver something, and that means when we deliver something, we can realize the value from that little slice. It's not everything, but it means we can deliver value as we go. The opposite side is doing big bangs. Oh, sorry, yeah, flood my line. Big bangs. If we do everything in a big bang, all the risk accumulates. So it'll take us the entire pointer doesn't work. The entire length of time in which requirements, business processes, the accountancy, the stock market, whatever, can change, in which we're not seeing any of the value. And in my experience, over the course of that time, something will usually go wrong and I'll get in trouble for it. Whereas doing things in small incremental steps, we will change massively what the direction is, but it means we are delivering on the value relatively quickly. Relatively. And again, it's really difficult to say what these incremental steps can be because we'll often hear about thin slices of value. What is a thin slice of value in this reference architecture? That will depend on your business and your context. It's really difficult to say, and I think that's something that we all have to learn with time by understanding the business we're operating in and the capabilities of it. Easier said than done. So, when we think about, and again, we're still talking about experiments and the cost of not iterating. When we're dealing with probabilistic and deterministic, as opposed to deterministic systems, in deterministic systems, given a set of inputs, we will always get the same output, right? In data, in the systems that we usually work with, we will get an output that can be sampled from a distribution, which means we need to understand broadly, not necessarily why or the causative factors, but we need to understand for our business use case how we can build our own model of what's up. Not our own model, but be able to predict for a given set of inputs, is it going to make us money as an output? Lots of maths, lots of systems involved, but that's almost always what goes in. We need to make sure there isn't some horrible risk of our chatbot being terribly racist, or recommendation system going off the rails, or whatever the case may be. And I will say, last time I gave a talk, a more astute mathematician than I did mention that chaotic systems are a type of deterministic system, which are really difficult to to deal with. So, chaotic systems excluded from this comparison. So, another thing to consider is the experiment value curve. There's so many different experiments we can run, so many different decisions we can make about our business, so many products we can run. How do we decide what experiments to run? Should we run our model A, the A prime, in an A/B test? Or should we look at, instead of changing our recommendation system, change the way we do email marketing? There is a tremendous space in which we can act. So I'm just going to give a little case study about a cybersecurity company I used to work, did some work for. No, I worked for, I was an employee. Over time, requirements are constantly being added. So they knew that they had a product that kind of worked. They were able to handle a few billion requests a day, which is good. But they also knew for what they wanted to do, this wasn't sufficient. They wanted to A, handle more capacity, but also B, make more complex predictions across a wider variety of features and a wider variety of model types. They wanted everything all at once. They had no plan for how to roll out incremental bits of it. And they had no benchmark to be able to say, okay, what is good enough? Because I'll come into different types of experiments later on, but there's different ways we can experiment if it's something good enough. The most important and damaging thing was they had no benchmark for what is good enough. They had no benchmark for what made their products good or bad at all. So it was doomed from the start for that, I will say. But the fact that there was no plan to deliver things incrementally, it was all one big bang, meant it took ages for us to learn the lesson of, oh no, this has gone real badly, even though it was fairly easy for a lot of us to predict early on, and certainly in retrospect to identify mistakes we made about this. So we know experimentation is important. We need to build systems to empower us to experiment. As I mentioned, we've got lots of different types of experiments. We can experiment with different models, we can experiment with different features, we can experiment with the same features calculated using different methods. We're talking about averages or means. We're talking about complex model-derived features from Model A and Model B. Loads of these at the technical level, and loads of these at quite high-level business processes around A/B testing or shadow testing. Not new into them, but there's loads there. We could do a whole talk on that. Understanding the different experiments is kind of key. This is, as a data scientist, or someone who started as a data scientist or more of a data analytics side of data scientist, this is something I spent a huge amount of time, many years learning about, and I never really wanted to. I know lots about Terraform, and all of it is against my will. It's important we make use of IAC tools. Being able to define things as code means when we make changes, when we try out new features, new tools, new LLMs, whatever, we can say, this is what we did. I think it was a popular scientist, Carl Sagan, or someone who said, it's not science if you don't write stuff down. This is one element of writing stuff down that we're doing. And there's many providers of this. Similarly, it's important to have data infrastructure. So identifying which elements of data we want to change, which bits we want to stay the same, having appropriate databases. Do we have OLAP, OLTP? Are we using everything in BigQuery? Are we split across multiple different things? Using dbt or an ETL manager? There is no right answer for these. They're all trade-offs, but these are part of the experimentation system, even if we don't necessarily consider them to be so. On the subject of ETL and ELT orchestration, this is an example of dbt, in which we can say, okay, we care about the outputs of the customer table, but things that go into that, the way we manage orders, the way we manage customers, and the way we calculate those will impact the outcomes of our experiments, which will impact outcomes at the business level, which again is really hard to keep track of and complex. But these are things that, even if it's not the primary thing to think about, need to factor into our thinking when we're building and designing these systems. When we're building, and again, there's so much about this that takes up time. We need to understand how we can automate a lot of this. And there are ways to automate all of this and any of this. We don't want to, if we try and perfectly design a system that can be automated for any task, we're going to end up making no progress. We need to kind of, similar to, as I mentioned before, say, okay, here's the incremental step we're going to do. We're going to say, okay, all of our models will be served from a Docker container using fast API code, and they will all, what's the phrase? They'll all conform to the scikit-learn .predict schema. Is that the right answer? Is that the wrong answer? Time will tell, but at least if we say this is where we're starting from, this is the opinion we're going to have, we can automate tools around those systems and explore that experimental space. Over time, if we decide, yeah, we've explored that experimental space, let's move on to the next iteration, we can do. But by being opinionated, we can make it easier to do the experiments that we think are useful and, experiment with them. Maybe we're right, maybe we're wrong. We need to experiment. Continuous training pipeline is a really key part of this. Being able to do training using the exact same code for training, both in model exploration, in offline training, and in online inference, means there is no mistakes happening between different areas. Data has to be available in our model at prediction time. If we're training our model using data that isn't available at prediction time, we have two options. Either we throw the model in the bin because we can't use it, or we spend a bunch of money and time building data pipelines to get the data available at prediction time. Neither one is a good option. This is one method of making sure we don't fall into that trap. Sorry, I realize I'm rambling. I'm not sure what the time is, but I'm gonna. Sorry, gone or left. Okay, I'm gonna go quicker. So, model evaluation is really important. It's really important to make sure we have clearly defined success metrics, and it's really important to make sure we have descriptive metrics, and also to make sure we're not getting the two mixed up. In terms of observability, this is one that often comes up in an ops perspective, and this is one where I think in the MLOps community we're more vocal about it. But certainly when it comes to LLMs and the concept of model traces is becoming more and more prevalent. Being able to see what happens at different elements and components of the system means we can debug and measure what's happening over time. So when I was working for an e-commerce retailer, we delivered three models accruing about £80 million per year. When I first started, it took about a week or so to deploy a model because there was no process that humans could agree on and no automated process. Within about 2 weeks, we were able to deliver models into production in about an hour. And by the time I left, we were able to do completely automated model retraining and deployment every day. So we've talked about automating some experimentation systems. How do we move from experimentation to production? The key thing is they shouldn't be two separate things. We can think about migrating and how we overlap between two systems, but I'm a huge... some people talk about throwing a model over the wall for engineering to implement. I'm entirely 100% against that. One thing that's happened in an awful lot of the organizations I've worked with is there'll be an argument about, okay, this is the way we do dev, this is the way we do prod. And I'm not saying we need, each of you need to go back and say and argue with your systems, sysops, platform engineering team and say, no, you're wrong. But data often doesn't fit neatly within the two categories of dev and prod. Data is often needs to be protected. It's sensitive, PII, commercial, whatever. Therefore, we need to use it, and we need to be careful that it doesn't leak into dev environments. However, we need to train our models with it, explore it with production systems, but we don't want to deploy it to customers yet. Therefore, it is both prod and not prod. Sorry, as I say, I'm going quickly. That is a complex thing, and we need to that's something to be explored within your organization. Working within your organization's policies. I'm not going to talk about notebook experiments because it's been done to death. Joel Gruss did a fantastic talk many years ago. Community talk, opinions have moved on, but it's always good. Continuous training pipelines are so important. I've spoken about them twice. This wasn't a mistake, this was intentional. We can look at doing shadow deployments. So deploying, moving from an experimental system offline, we want to test and see how it works in production. Is the latency okay? Are the predictions that we're making of the expected, within the expected distributions? If we break it down into different subsets of consumers, are we able to, are we seeing the predictions of value we expect from different consumer groups? All of this we can do in production while serving the model, but not actually using the outputs of the model for the customer. We can just kind of make the predictions and then look and then analyze them later. This is Shadow the Hedgehog, by the way, so it makes sense. It's always important to be able to say, okay, we made an experiment. It succeeded, or far more frequently, oh no, this didn't work. Let's roll back to a stable state. And the thing that I hate the most, possibly in all of data science and engineering, is deploying a model that relies on a particular way of calculating new features. So we deploy a model, we deploy a new feature pipeline, then we realize the model isn't working the way we anticipated, which happens, and then we redeploy the new model, which is using, we redeploy the old model, which is using the new feature pipelines, which isn't the exact way that those features were trained on for the original model. So we have a mismatch, and it's just a massive pain. So the last thing you want to be doing that is at 2 a.m. in the morning when you've got a P1 and your model is failing, having good systems to have stable fallbacks and rollbacks. My favorite fallback is if a model breaks, we can just get a standard tinned, canned average answer. So in a binary system, we'll always just pick category A, in which we will miss out on a lot of potential revenue, but it's not a catastrophe. And it's, the simple engineering credo of keep it simple.
Sorry, what about having like 5% random decisions as part of the fallback?
That's a really good question. I don't like the idea of randomization in a fallback because if I'm falling back, I want it to be really reliable. In terms of going forward with different deployments, absolutely, but not so much for fallbacks. Feedback loops, pretty much everything I've been discussing is feedback loops. We learn something, we do something about it. We do an experiment that gives us future hypotheses for us to test. I could have done the entire discussion on this. I will in future do an entire discussion on this, but it isn't just tools and tech, it's people. It's all of us who use the technology. Tech is easy, people are hard. If we're building these platforms, we need to make sure it's easy for stakeholders to use, whether they be data scientists, product owners, chief executives, whomever. It's got to be easy for you to use for different people's processes. Not only must it be easy to use, but people have to want to use and they have to buy in. It's really hard to do that sometimes. But as ever, it's about working with people, understanding where they're coming from, compromising and moving on. Often it's about cross-functional teams. We end up with people with different skill sets. I think most of us here are from more of the data background, but oftentimes, say, when I've been working with recommendation systems, I've been on teams with UX designers, with front-end developers. I know nothing about front-end dev. I learned HTML a tiny amount when I was 14, was disgusted by it and never went back. There's nothing wrong with it, it's not my cup of tea. But being able to work with different folks, understand their perspective, and make sure that what we're building conforms to their needs is vital. And similarly, they need to compromise with us as well. It's not a one-way street. We need to balance experimentation with maintenance. So again, as I mentioned, like Leanne earlier on did a really good point about these are the elements of data science systems that are often ignored. But if we're going to maintain and operate them, that's what's going to be happening the majority of the time. If we've got a successful system, it'll be automated in the background. We need to make sure we can maintain things while at the same time building out new ways of doing experimentation. Oh no. Okay. All of this experimentation requires leadership buy-in. That is making sure they're incentivizing testing and learning from failure. Again, as Leanne said earlier on, 80% of experiments fail, but that's not necessarily a bad sign. That can just be part of the process if we understand that. And making long-term incremental bets, not just, okay, we're going to have a sprint in which we deliver some slice of value. That's important, but it's not sufficient on its own. We need business to understand over the long term we will increase our capability around experimentation, around data products. Thank you. We will increase our capacity around data products, and if that goes well, it can be eventually an exponential growth as opposed to strictly we can do this and that's all we get. It's a whole system. So, what conclusions can we draw? So, as I said at the start, experimentation is really important. We need to iterate. Business KPIs and model metrics need to be going the same way. It's really important that we have, again, as Leanne said, the North Star of knowing where we're going and making sure that the models that we're training are aligned to that. If we want our business to make more money, make sure our model metrics are aligned to make money go up. It's easier said than done. The worst client I've had in terms of, lovely people, but in terms of success of a project, in terms of success as a business, was a business who didn't have a clear idea of what their business KPIs were, what made their product good or not. How can we build a good model? How can we build a good model without knowing what good is? And I don't believe there is a way. Despite many people trying over the years, I know from folks who still work there, they still don't know how to measure what good is. And the second thing I want to say is the key point is start from where you are. There's all these fancy architectures, there's all these fancy ideas, and many people are much smarter than me doing fantastic talks. And a lot of these concepts can deliver a huge amount of value, but the key isn't to do the fanciest thing, it's to do the most useful thing, at least in my opinion. I'm going to leave it there. Thank you very much.